Hello, everyone. I'm Octavia, and I will be presenting some interesting stuff about data augmentation. I am a machine learning engineer at FlexJobs currently, but I have worked with, I've freelanced as an NLP data scientist and engineer for various startups in both the East and West Coast in America and bigger companies. And I've been a researcher, computational linguistics, natural language processing, machine learning researchers at two different universities in Europe, and Bitdefender, an antivirus company. And I have a pretty complex background. I have a computer science background, but also a linguistics background. So best of both worlds. Okay, so at FlexJobs right now we're doing a lot of text classification for using deep learning methods, but I wanted to talk about something that a smaller project that I did for Lark, which is a very quick and interesting project. And I want to talk about what you can do when you don't have enough data to use highly sophisticated deep learning methods like the BERTs and the transformers. So I was contracted by Lark in 2018 to help them with their food logging functionality. And my help is now still being used in their app today. So let's go through it. Lark is a really nice startup that has an app with the long-term goal of creating preemptive AI for healthcare. So it feels like a virtual assistant, specifically a virtual nurse. But it's basically a chatbot. It doesn't have, or at the time when I worked with them, it didn't have natural language generation capabilities. So I wasn't using any sort of transformer stuff. Right, so what was the problem that I helped them with? So they had a functionality where the user would input what meals they ate that day for the purpose of figuring out if they are on track with their diet. It's usually it's targeted. Their user base is people with health conditions, chronic health conditions that can be helped through diet. So people with diabetes, type 2 diabetes, and hypertension. And so they already had in place a food database with nutritional information about different meals. But they didn't have a very solid way of searching. Like, they had a way to search through the database and retrieve that information and form programmatically rule-based, form an answer explaining to the user what the nutritional components of the meal that they just had are, and tell them how they could improve their diet. However, what they didn't have was a way to parse the input when the user would say that they had multiple meals that day. So an example, like if a user would input just one single meal, let's say, and we use meal here a little bit. We use it with a lot of liberty. But yeah, if a user would say something like black coffee with sugar, they already had a machine learning model in place that could identify that the sugar was an ingredient of coffee. They also had in place a model that could identify that in Diet Coke, diet modifies Coke. However, when they had multiple, as I mentioned, when the user would input more than one meal in one single line and hit enter, they had no way of knowing that Diet Coke and banana ice cream were separate meals. And so their two models would identify that banana was an ingredient of Coke. So Lark's temporary solution before I came in was to ask the user to input 1 meal per line, which is very cumbersome, as you can imagine. And I think if any of you have ever used a similar app or website that helps you track your diet and for health conditions or for your weight loss journey, whatever it is, however you stand on that spectrum of body positivity or health wellness. If you've ever used that, you probably would know that the user interface of like actually inputting the food is pretty cumbersome, because you either have to look for the look yourself for the food item, or you have to select from a drop-down menu. It's pretty annoying. So I came in in May 2018, and my project was for 4 months. So what did they have available in order for this problem to be solved with machine learning, specifically natural language processing? They told me that they had 13,000 pairs of user food input and human annotated splits. Obviously, as we all know, as data scientists and machine learning engineers, we know that what the stakeholder tells you is the data size is not really the data size, because they usually have duplicates. So after I removed the duplicates and the semi-duplicates, I ended up with only 9,000 examples. So 9,000 examples is considered a very small data set. So it's definitely not something ready for deep learning. And another thing to mention here, as a researcher with my background in research, I was a little vexed to find out that they weren't looking for annotation agreement. So normally, if we think about machine translation, for instance, in whether deep machine translation or classic machine translation, we have we're looking for more than one annotator to annotate the same, to translate the same pairs, to make sure that there's some sort of agreement. Especially for sequence labeling. So there was no annotator agreement. Basically, the 13, 15 people, the engineers that worked for the company, because it was an early stage startup, like a B stage. They just each got a bunch of inputs from users, actual real life inputs, and they decided what the meal split would be. So we all know in supervised machine learning, you learn a function describing the relationship between a given set of example input and tag pairs. So we predict the tag of a new input, and we test the accuracy of the prediction on a separate set of input tag pairs not used during training. We know this. Also, I had some background in problems similar to that coming into the project. So I did some work on named entity recognition, or named entity translation, specifically with word embeddings. I did some celebification, which I know might not seem like it's related, but it is. It also works with sequence tagging. And I also use sequence tagging in some morphology, computational morphology problems. So coming back to the problem, based on my experience, I immediately could tell that this was an issue similar to named entity recognition. So in named entity recognition, for anyone who's not aware, I imagine a lot of you are, I hope, you would have a problem like you would be given a sentence like, the US president spoke in Washington state yesterday, and you would want to know which one of these words represent an entity, the name of an entity. So in this case, the output would be a label for each word, which would say whether that word pertains to a named entity or not. So the relationship between the input and the output tags would be a one-to-one relationship, which is different from machine translation, where you have like a sentence pair, right? The target language, the source language and the target language, and it's a many-to-many relationship, because a group of words can translate into one single word in a language, or vice versa. So yeah, so in this case, the tags that are possible are O, representing outside of the word being outside of a named entity, B as in from beginning of the named entity, and inside as in inside of the named entity. So in this case, US president would be a person, or maybe an organization, depending on how you view it. And then Washington State, again, would be either a person or an organization, or a location, depending on how you think of that, but they're both named entities. So for our meal splitter, we would receive an input like black coffee with biscuit and banana split ice cream. And we would be able to, I mean, the people who annotated this, decided that the biscuit was part of the black coffee. So they said black coffee with biscuit is one meal, quote unquote. And then banana split ice cream is a different meal. Again, they're desserts and beverages, but we're going to stick to the generic meal. So in this case, we would receive black coffee with biscuit and banana ice cream as the input from the user, and the model that I would hope to create would be able to accurately predict that the tag sequence would be BII, OBII. So basically, the split would happen at the B, each B. What I got from the label data set of 9,000 examples was, I'm not sure if you can see my mouse, but would be this intermediate, this part that's already a list of substrings, and then from that list of substrings, I deduced from the combination between this and the list of substrings, I deduced this IOB tagging, as it's called. So of course, I think this is a very important question, which I feel like a lot of people in NLP tend to forget. I feel like sequence labeling is a problem that's not as used or employed or thought of before proceeding in solving an NLP task. And people usually go with, oh, it's a classification. So the question here is like, when I came in and I proposed to the startup team, hey, this is the engineering team, this is what I'm going to do. They're like, wait, why isn't it classification? So yeah, why not use three-way classification? So predict that a word is either I, O, or B. And why not use that instead of sequence labeling? So the state of the art for named recognition is achieved when the task is treated as a sequence labeling task. The reason, I mean, I tried, for their sake, because they were software engineers, they were machine learning engineers, so they didn't have experience with this. But for their sake, I tried to use a multi-layer perceptron and an SVM classifier, specifically a classifier, not a sequence labeler, using the previous and current words as context, as the features, using words of concatenation, and the results stagnated around 75% F1. Now, if you were not a machine learning engineer or researcher or ML data scientist or something, and you didn't have experience with this, you would probably think that, oh, 75% F1 is like good, maybe we didn't get the right features, and so we should just look for better features, or we should do some hyperparameter optimization or something to get it better. But in this case, it's actually, it stagnates because the problem isn't formulated right. And specifically what happens is there's data leakage that occurs when you shuffle the data and you split it in train and test, because I got 9,000 examples that were not, were not set into train and test. I had to do that myself. So when you do that, you end up with, if you think about black coffee with vanilla ice cream or something, there's going to be a B label that has black as context and with as context as well. And then in a different instance, it might be also coffee, or similar words might be in the context of another label that's like an I or something. So in that situation, you basically have the same features that connect to different labels. So it's very confusing. Also, for people who are aware of this and have bumped into these types of problems, you know that it's sequence labeling is the best way to go when you have a problem where the labels, the probability of an element in the sequence receiving a label is determined by the entire sequence, like before, and it's not just like a window, it's like of the entire input. So state of the art, of course, this is state of the art at the time when I was solving this problem. So in 2018, it was bi-LSTM, bidirectional LSTM, with CNNs, I'm sorry, and conditional random fields. This was the state of the art then. I decided to go with bi-LSTM and CRF just to see what happens, because I felt like if I added another deep neural network or neural network to the mix, it would create more depth that required a lot more training data. So I really wanted to stick with the most simple model that I could get so that I don't overfit. And before that, there was the bi-LSTM CRF, which was like, you know, like before, like it was the best before that. And then before that, it was the conditional random field. Conditional random fields, which are like Bayesian networks. They are similar to, they can be considered kind of like single layer perceptron, I guess. Yeah, like logistic regression is like you can prove that logistic regression is a subtype of conditional random field, and logistic regression can also be viewed as a single layer perceptron. So there is this neural network connection, but it's not like fully there. So we'll look at the models so we can see why they work. So why do bidirectional LSTMs work for named entity recognition? So again, when I say present day, I meant back then. So the most updated flavor of recurrent neural networks, as we know, are known for modeling long-range feature dependencies between words in a sentence. So this is useful when you want to model how sentences work. The bidirectional aspect of LSTMs is useful also for modeling dependencies between words in languages, and you can think of why you would need both directions to occur. And I think a really good example is German, where you put the verb at the end of the sentence, and you have to kind of read the sentence until the end to find out what the predicate is, and then go back to like focus on the object. So there's that like backwards direction that kind of matters. So this is kind of what it should look like. So if we get an input like black coffee and cake, and we want the output to be the sequence to be labeled as a BIOB. So black coffee is an entity made out of 2 words, and then cake is just one entity, and then this is outside. And so we have this like forward and backwards relationship that is being modeled by the bidirectional LSTM. Now, conditional random fields, on the other hand, focus on the relationship between it's an undirected relationship between the labels. So if you look at this, you could consider this bidirectionality of this type of LSTM as a sort of undirectionality. So the going both ways is just as if it was undirected, just like here, except that here it's between the labels, and here it's between the, you see this is like going this way. So it's modeling the input rather than the labels, the output. So when you combine them, you kind of almost get this sort of very close to what a fully connected, like a feed-forward neural network, kind of like a fully connected neural network would do, since there's the relationship between the output that is being modeled, but also the relationship between the input, which kind of explains why something that I glossed over here, the state of the art after this, like they were able to get like recently a little bit better, like a small improvement in accuracy for named entity recognition when they used BERT, which is a transformer model, so a feed-forward, fully connected neural network. So it kind of, but it's trained on a lot of data, so it kind of makes sense. There's a pre-training aspect about it. Okay, so let's see what happened when I used this bi-LSTM conditional random field model on the 9,000 examples. Obviously, I overfitted. And this is to be expected because I tried my best to have this model be as simple as possible, such that I would avoid overfitting. So one thing was making sure that I had not that many neurons. I only had one single layer of a bidirectional STM, as shown here. I believe the neuron number was maybe like 20 or 15, like something ridiculously small. I still had an overfitting here. So what was happening? I try to make sure that it was an issue with data and not an issue with the model itself. And it looks like when I, gave it more and more data over, like I trained it with 30% of the data, sorry, with, 30% of the data, 40, 50, 60, 70, and then 100. It looks like the trend for the validation F1 score, I believe. Well, I say accuracy here, but I think it was F1. It was improving. So that meant that it was indeed the case that I just didn't have enough data. So this is where things get interesting, and this is where it goes into weak supervision, semi-supervision, data augmentation territory. And this, I was doing this, I think, a few months before the that really cool paper from IBM on the project debater, the Will It Blend a paper where they show that if you blend like weakly labeled data with strong labeled data, so data that is labeled through a heuristic versus data that is labeled by humans, if you blend that, then during training, then you get like better accuracy or better scores than if you were to just put them together and not blend them. So this was before then, so I couldn't come up on my own with that idea. So what I did was I did augment the data set. So how would you do data augmentation for this sort of task? Because normally when we think about data augmentation in computer vision, the problem is a lot simpler. So a lot of people do apply filters to the image or flip the image or reverse the image a little bit depending on the problem. If it's like a digit, like identifying the digits in a drawing, you'll in a handwriting image, you can flip it a little bit, but you can't flip it fully, because if you flip a 9, it turns into a 6, like on the horizontal axis, right? So you want to rotate it a little bit. So, but in certain other instances where you're like doing classifications of cats versus dogs, you can flip the image and it's still going to be like vertically or horizontally, and it's still going to be a dog. So, so can you do what sort of things can you do in the case of this NLP problem? So I leveraged something called collocation statistics, or what I called collocation statistics. So I had, I looked at what was the occurrence of, what sort of patterns I saw in the training data, right? So I saw that I had a lot of single and 2-word examples. So I had a lot of Bs and a lot of BIs. So I just created 70,000 examples from combining 2 BIs to form BOB, so coffee and cake. Which would require 2 separate searches in our database. And then also BBs, coffee cake, which coffee cake, it could be a cake that also has coffee in it. But yeah, so this is why we call this weak labeled data. So I also created BBs and BIs to form BI, BI, and BIO, BIs. So this is a safe combination. However, with this, I was able to increase the F1 score. a thing to note here, we obviously were always optimizing for F1 and not accuracy because we have multiple, it's not binary, a binary classification. We did, I did turn it into binary classification later, but I mean, not classification, but binary classes. And then I also added another strategy to augment the data. So I did, I got an extra 1.5 thousand examples by reversing some of the existing data. So for instance, I had BOBI, and I would flip it around. I would consider that the O, the outside word, which usually was an and, I consider that to be the axis, right? If you think of it as like an image, the and was the axis around which I could flip the image. So BOBI turned into BIOB. So black coffee and cake turned into cake and black coffee, essentially. And when I did that, the F score improved even more and went to 88%. Now, what I had to do to get it to the point where the team was comfortable in deploying this was realize that the O's were really unnecessary. The outside words were unnecessary since there was already a stop word stripping phase before before doing a database search. And so I really didn't need to tell the rest of the pipeline that I discovered a stop word since that was already eliminated. So I decided to remove, so instead of having it be a sequence labeling task with where the labels that were being predicted were either B, I, or O, in this case, I turned it into a task where it was either B or I. And so the O turned into an I. So in this case, like if I had black coffee and cake, black coffee, and it initially was BIOB, that example would turn into BIIB. So this and would be like considered part of the first entity, the entity before it. And that way I still had a good split here. So yeah, so that improved the accuracy to 90, the F1 score to 90%. Now, this is what happened when we actually did that. We no longer see a bit like a clear underfitting like here, overfitting like here. See, there's this intersection here where the validation becomes less performant than the training, which is a clear indication of overfitting. So here we kind of like see that they're meeting. They're starting off a little higher, but they're meeting, and yeah. So what I've learned from this, and then we deployed this, and now this NER model. I mean, last time I checked in with them in 2000 and last year in 2020, they told me that they're still using a similar approach. Obviously, they wouldn't say how similar. They wouldn't say if it was exactly the same model or slightly different. But yeah, but the plan once they deployed it was that they would give the user this suggestion of like the user would input, would just write free-form text. Today I had la 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 la, and then my model would come in, would make a prediction for a split. Then that prediction would be used for the actual split. So they would the string would be split after every B. And then that split would be shown to the user. So the assistant, the nurse would say, hey, it looks like you had this and this and this. Is that true? And then the user would be given the option of saying, yes, that's true, or no, you didn't get it. And then they would be asked to input one meal per line still. So that way they got more labeled data by the actual users. I don't know how reliable that was, but right. So my conclusion from this is word classification models are prone to data leakage and also stagnated around 75% F1. So in case someone was not familiar with The concept of sequence labeling, which is also present in, is used in computer vision for object segmentation. So figuring out of all the pixels in the image, which pixels belong to a class. So if people, some machine learning engineer out there was starting out and was unaware of this type of problem, and they would have gone down the word classification path, they would have stagnated. They would have not been able to cross 75. And that is my timer, sorry. And then initial runs of the NER, the CRF model, stagnated around 85 F1, but the learning curve trends seem to suggest improvement with additional training examples, and data augmentation really got us to the finish line. So yeah, human performance for this task is 96% F1, so we got pretty close. And these are the people I was mentioning earlier. Thank you. Questions?